Hi everyone, I am Masoomeh Javidi Kishi. I am presenting FWKV, which is about improving read guarantees in parallel snapshot isolation. This was a joint work between me and my advisor, Dr. Palmieri, and we have done it during my PhD studies at Lehigh University. I want to first focus on consistency levels in a distributed setting. Consistency level plays a role when there is an access, meaning read or write, to shared data. In order to answer this question that asks, what is the right or what is a proper consistency level for a target application, we need to know first what are the requirements of that application. For example, if we have a bank application, we need a strong consistency level. The data of accessed bank accounts need to be fresh. On the other hand, when we deal with a social media application, we prefer to go with a weaker consistency level for the sake of performance and scalability. Therefore, the level of data freshness can be compromised here and it can be relaxed. This is an example for a bank application. We have a distributed system that includes two nodes, node 1 and node 2. We have, suppose, two saving accounts, saving account A and saving account B. And at the beginning, there is $0, no amount, in saving account A and saving account B. And suppose that these two users, user A and user B, would like to have in total $20 in both saving account A and saving account B. Sorry. User A starts transaction TA, reads saving account A, saving account B, $0 in both, and user A deposits $10 in saving account A. So when transaction TA commits, we have $10 in saving account A. Later, after TA is committed, TB starts by user B and it reads saving account A, saving account B, fund, and it finds no money there. So user B deposits $10 in saving account B. So at the end, we have $20 in total in saving account A and saving B, and this wasn't desirable. Therefore, TB should access TA's should access TA's snapshot. Now, in this slide, let's see an example with a social media application. Again, we have two nodes, node 1 and node 2, and two users, and each user can post on his or her own wall. User A starts a transaction. It reads post B1 from user B, and then user A updates his or her own wall with a new post, meaning post A2, and commits. User B starts another transaction, meaning TB, in this slide, and finds post A1 from user A and updates his or her own wall with a new post, meaning post B2. Sorry. From the perspective of user A can find first his or her own post and then user B's post. From the perspective of user B can find his or her own post first and then user A's post. And this is fine because any order between their posts is accepted. But what if users of social media application want to read news on the social media application? Here, accessing outdated data is not desirable. On the other hand, a social media application still doesn't want to go through the overhead of using a strong consistency level. And that is where our work, FWKV, is motivated. In FWKV, we want to retain high performance and scalability of a weaker consistency level, but at the same time, we want to improve the level of data freshness of read operations of read-only transactions. Before going to the details of our work, let's see one of the state-of-the-art protocols, Walter, SOSP 2011, in a nutshell. Walter provides parallel snapshot isolation consistency level, or PSI. PSI is a suitable consistency level for social media applications. Walter, by using PSI, enables efficient communications. This efficiency comes from replicating data asynchronously. Basically, each object in Walter is assigned to one or more preferred sites, and every update on a specific object can be committed by only checking or accessing preferred sites for write-write conflicts. And if we find no write-write conflicts, then we can allow propagation of committed transaction to non-preferred sites asynchronously later after committing the transaction. So, as a conclusion, Walter provides efficiency in terms of communications, but on the other hand, it also allows to observe obsolete version of data. The right plot here shows that the performance of a PSI protocol such as Walter is much better than the performance of a strict serializable protocol. This example shows the usage of vector clocks in Walter protocol. Here we have two nodes, node 1 and node 2. Each node in Walter is assigned with a vector clock, and the size of vector clock is equal to the number of nodes in the system. Suppose we have object X and object Y. For each object, we can have a set of versions, and each version of the object is also associated with a vector clock that comes from a vector clock of a transaction that committed, that updated or created that version of object. If one transaction T1 starts here on node N1, it assigns the vector clock of node 1, meaning 4, 5, here to its own vector clock. And based on this vector clock, T1 is able to access different keys. For example, for reading X, T1 is able to access X0 because the entries of the vector clocks of version X0 has lesser or equal entries of the vector clocks of the entries of vector clock of T1. For accessing Y, instead of picking Y1, T1 is able to pick version Y0. The reason here is that the entries in the vector clock of Y0 are lesser or equal than the entries of the vector clock of T1. It cannot access version Y1 because, as you see, the second entry of vector clock of Y1 has 6, and the second entry of T1's vector clock has 5, and 6 is greater than 5. In this slide, we wanted to show that how read-only transactions in a PSI protocol can read obsolete data. We have 3 nodes. The size of vector clock for each node is equal to 3. On node N2, we start transaction T2, and transaction T2 wants to update key X with a new value X1. It updates X to X1, produces this new version X1, commits, and increment the second entry of N2's vector clock from 6 to 7. And as we said, The result of this commit can be propagated later to different nodes which are not preferred sites of key X. Suppose that node 1 receives the outcome of T2 sooner than node 3. Once T1 starts on node 1, it has the information about the outcome of T2. That's why T1 can read the latest version of X, meaning X1. But since the outcome of T2, when T3 starts, still has not been received by N3, therefore, T3 is able to pick X0 instead of X1, the latest existing version. So, as a result, T1 can read fresh, but T3 reads old in this example. The reason of being conservative in PSI with respect to picking the correct version is shown in this example. We have 3 nodes. On node N1, T1 starts, it assigns the vector clock of N1 to its own vector clock, and it wants to read X, it picks X0 because the associated vector clock to X0 has lesser or equal values in the entries. So it picks X0. Concurrently, if one transaction T3 updates X and Y with newer version, meaning X1 and Y1 and commit, then this newer version in the second entry has timestamp 7. If T1 wants to read Y and it picks Y1, then as you can see, because of reading X0, we have an anti-dependency between T1 and T3, and we have a direct dependency between T1 and T3, and this is not accepted in a PSI consistency level. So our solution is to use an additional metadata, which we call it version access set. So by adding this metadata, we are able to track anti-dependency relationships among transactions. So tracing concurrent transactions that overwrite versions read by read-only transactions is possible. Read-only transactions can log their information into version access set of their read objects. So based on that information, read-only transactions are able to pick a fresh and also a correct version of key or object. And update transactions also here in our protocol propagates the content of each version access set to their newly produced version. When a read-only transaction commits, it sends a remove message in order to clean the version access sets of dependent objects. The outcome of our protocol is that here, similar to Walter, we let read-only transactions to be abort-free, but we also let read-only transactions to read the latest version of access objects if visible and if it's the first time that the node is contacted for accessing one specific object. And in our protocol, update transactions also are able to access the latest version visible. However, still they can abort because of observing anti-dependencies later. This slide shows how read-only transactions can be controlled in FWKB. We have 3 nodes in this example. Transaction T1 starts and it wants to access object X. It sends a read request to node N2. It picks X0, which is the latest existing version, and it puts its own fingerprint in version access set of X0. Also, it updates the second entry of its own vector clock. If a concurrent transaction T3 updates X and Y with X1 and Y1 and commits, this update transaction propagates the fingerprint of T1 into the version access set of X1 and Y1. So later, if T1 decides to read Y and sends the read request, T1 is able to find its own fingerprint in the version access set of version Y1. It doesn't pick version Y1, instead it picks version Y0. At the end, T1 sends a remove message in order to clean up version access sets of X1 and Y1 and X0. This slide also shows how update transactions are controlled in FWKV. We have two nodes. Update transaction T1 starts. It can pick the latest existing version, and it can update the vector clock, its own vector clock, at the second entry with timestamp 7. And since here, T1 was able to pick the latest existing version of X, when it decides to write X, it can commit instead of aborting. In a PSI protocol, T1 aborts because T1, instead of picking X1 and updating its own vector clock, it picks X0. So it aborts instead of commit in a PSI protocol. But if the FWKV allows T1 to commit. Here we show our evaluation studies. Our experiments are done using 20 physical machines. Each machine has 28 Intel Haswell CPU cores and 256 GB of RAM. Nodes are interconnected using 10 GB per second network, and in each node we have 5 client threads. We use 20% read-only workload and 50% read-only workload. We use two types of benchmarks, YCSB and TPCC. In YCSB, we have two transaction profiles, one for update, one for read-only. In update transaction, we read 2 keys, and those keys also are written. In read-only transactions, only 2 keys are accessed. We configured YCSB one time with 50K keys, another time with 500K keys. TPCC has 5 transaction profiles, 3 update profiles, and 2 read-only profiles. In terms of the competitors, we compared FWKV with Walter and two-phase commit baseline. So both FWKV and Walter are PSI protocols. Two-phase commit baseline is a strict serializable protocol, and it's stronger than PSI. This shows the result of throughputs of YCSB benchmark when we compared FWKV with Walter and two-phase commit baseline. And we use 5, 10, 15, 20 nodes. So more nodes here means more contention. And as you can see in the plots, up to 10 nodes, the performance of FWKV matches with the performance of Walter. But when the contention increases, the gap between FWKV and Walter also increases. Here, this gap is because of 2 reasons. First, FWKV goes through more synchronization steps. Second, the size of version access set increases when we have more contention. So in this plot, when we have 20% read-only transactions, using 50K, the gap between FWKV and Walter is 20%, and using 500K keys, the gap between FWKV and Walter is 16%. In the right plot, when we have 50% read-only transactions, using 50K keys, the gap between FWKV and Walter is 15%, And using 500K keys, there is no gap between Walter and FWKB. In this plot, we measured the average size of version access set or anti-dependency collected during prepare phase of update transactions. The x-axis shows the number of keys in YCSB benchmark. We injected 20, 15, and 80% read-only transactions. Using 15Ks of object, 50Ks of objects, we have an extreme contention. So because of that, a lot of information needs to be propagated during committing update transactions. But when we have a 500 keys, the size of version access set is 0. And finally, in this plot, we compare the throughput of FWKV, Walter, and two-phase commit baseline using TPCC benchmark. Again, by having different number of nodes, we also change the number of warehouses per node. One time we set it to 16, one time we set it to 32. And this experiment, in general, in TPCC, because update transaction doesn't necessarily read the same key that they want to write, so update transaction can get a lot of benefit in using a PSI protocol in comparison with a two-phase commit baseline protocol. So because of this, we observed a better performance for PSI competitors. Using 50% read-only transaction, there is only 5% gap between FWKV and Walter. And when we have an update intensive workload, meaning 20% read-only transaction, the maximum gap is 20%. Thank you very much for listening to my presentation. And please reach out to us with any questions. Thanks again and have a great day.